Section 1.3 is going to be evaluating limits using algebraic techniques, okay? So finding limits using a graph is great, but some functions are pretty complicated or time-consuming to graph accurately. So we are going to discuss different algebraic techniques that can help you evaluate them, okay? So these won't always be super quick, but remember, making a graph by hand is not always your choice. So quick tips. If a graph isn't provided, then you should probably use algebraic strategy, okay? You don't want to graph these by hand, and you would not have a calculator available to do limits, typically, on an AP test. So some of the strategies, and I do these in order. First, you try substitution. As long as the limit is defined, then that would be the y value, all right? So defined, it's okay. If it does not exist, then keep going. Try another option, keep going. All right, well, if substitution doesn't work, then you want to try to factor, cancel, reduce, things like that. If that doesn't work, then you kind of need to make a table, but this is a quick table, and if that was your forced strategy, your options are infinity, negative infinity, or if they don't agree, it does not exist. This is not a long, extensive table because you would have to do this by hand. And number 4, there's something called indeterminate forms, and we're going to learn a strategy for that later, okay? Much later, like after Unit 2. All right, the problems are going to be all mixed up. So for right now, I'm going to separate them so we can see them in practice, but on the homework, you won't know which strategy is which, okay? So strategy number 1, you always want to try direct substitution, all right? So like here, if I substitute -1 for x, as long as my value is defined in the denominator, then this is going to be my y value, all right? So -1 minus 1, -2 minus 6, and we reduce that. And that's going to be our limit value, okay? On example number 2, if we substitute -2, I would get 0, which means it's undefined, okay? So what I need to do is I need to try another strategy. So try another. Okay, and we'll come back to this one. So, warning, if you get one of these forms, these are called indeterminate. And the way I kind of describe that is that there's some math happening in the problem or the function itself that actually hides the limit value, okay? If you can use some of the algebraic strategies we're going to use, we talked about in this section, then that's fine, but there will be some examples where we're going to learn an entirely different procedure. But we have to learn a lot more calculus before we can come back to that idea, okay? So indeterminate, we'll be speaking in about 2 months again on this. All right, so strategy number 2 is factor and reduce. So if substitution doesn't work, then try factoring. So let's go back to that example number 2. Well, I think these will factor. So I'm going to get rid of this because it was undefined. And that's what I mean by there's some algebra that's happening that's hiding our limit. So we need to factor trinomial. The factors of 8. That will add to give us -2. And so these reduce, which produces a hole in the graph. And so really it's going to be the shape of x minus 4. And so now I want to try the problem again. So I've got the limit as x approaches -2 of just x minus 4. Okay, so we can't really get rid of that because that does affect our graph with a hole, but that doesn't change our limit value. So now we're going to try substitution again. So we don't have a denominator, which means our value should be defined. So -2 minus 4 means our limit value is -6. Okay? So let's come back to these problems. And I just did it here. All right, let's look at the next one. Well, we have a cubed. So as a review, I'm going to do the numerator. We get x minus 1, x minus 1. And then this is the difference of cubes. So I factor, this is a good review, it's called SOAP. So you always want to think of this as x cubed minus 1 Q. This is like A and B. So when you factor these, it's A squared, A times B, and B squared. Now, the way our signs work, that's how SOAP comes in. So S stands for the same. So this sign is always the same as what it started. The next sign is the opposite. And the last sign is always positive. Okay? Quick review. I'm sure everybody forgot this because, well, you learned it a while ago. So on this problem, we're going to have x, because that's A, x minus 1, x squared, plus 1 times x, plus 1 squared. Okay? So then these terms reduce, and I'm really looking at the limit as x approaches 1 of x minus 1 over x squared plus x plus 1, which is defined now. So 1 minus 1 is 0, and then 1 plus 1 plus 1 is 3. 0 can be on top. 0 is a good limit answer. 0 just cannot be in the denominator. Okay? All right, let's explore when a table is necessary, so you don't spend a lot of time using values and time that you don't need to. So you want to try this when substitution doesn't work, factoring doesn't work, but you still get 0 in a denominator. So that means that you will have a vertical asymptote. And so what's happening is it's a rational function. So we either have 2 going to positive infinity, 2 going to negative infinity, or 1 of each. Okay? And so that's why we just need to figure out if they're positive on top, negative on bottom, things like that. So let's look at example 5. Well, if I substitute 2, I get undefined. It doesn't factor and reduce. So that's when I know a table strategy is our go-to. Now, 2 is our target. So I just ignore this, okay? So what I want to do is I want to plug in something that's smaller, and then I want to plug in something that's bigger, okay? And I try not to go too far in case some other things are happening. But if I plug in 1.9, all I want to do is I don't want to find the exact answer. I just want to find out if it's going to be a positive or a negative. So I would have a positive and a positive on top. Oops, sorry. And then on bottom, I'd have 1.9 minus 2. That would give me a negative. And so what happens is we're going to go to negative infinity. Our graph would be going down to the left. And then the same thing. What if I plug in 2.1? So I'd have a positive on top and a positive on bottom. And so that graph would be going up. And so really what's happening is here's 2, is from the left, we're going down, and from the right, we're going up. So since these two don't agree, and it's a double-sided limit, that's when it does not exist, okay? So don't get bogged down in the actual values. You're just figuring out what the signs are going to be. All right, let's try example 6. Well, I see a bunch of squares. So I'm automatically thinking, yep, if I plug that in, I have 9 plus 9 is 18, minus 18 is 0. So we are going to factor. So x, 3 and 1, that would be x plus 3, x plus 3. So these reduce. And then if I try plugging in negative 3, it's still undefined, okay? But I'm going to write it nicer. Same idea. So I want to try a number smaller and a number bigger. I'm sorry, that's bigger. That one's smaller. Okay, you know what I mean. All right, so if I plug in negative 2.9, I have a negative on top and a positive on bottom. So that's negative infinity. And then if I substitute negative 3.1, I'd have a negative on top and a negative on bottom. So these don't agree, and it does not exist. Okay? Now, trust me, it's not that it will always not exist, so just make sure you're making your table to check. let's look at our next one. If we substitute, we get an undefined. If we don't factor, so we're going to go straight to our table. So I'm going to plug in negative 0.1 and positive 0.1. So if I plug in a negative, anything squared is going to be positive. So I have a positive over a positive. And then if I plug in a positive number, it's also positive over a positive. And so since these both agree, we're going to get positive infinity. Okay? All right, there are some special cases that look like this, and they typically involve radicals, okay? Trig functions will also be special, piecewise, limits of infinity, but the first special case that we're going to talk about are roots, okay? And it's usually a root plus another root or a plus another number or minus, but it's two different terms. And so we're going to call this the conjugate strategy. So this will take a little bit of algebraic work, but it's also good review, okay? So if I substitute 0, well, that's undefined. So I can't factor. So what the conjugate is if you had, let's say, A plus B, the conjugate keeps the first term the same, and then you always switch the sign of the second one, okay? So on here, we're going to have root x plus 1, and we're going to put plus 1. And now if you multiply it by the numerator, you do have to do it by the denominator. But you always want to leave the denominator alone in factored form, and you always want to simplify the numerator. Okay, so this takes a little bit of review. So I still have my limit. I'm going to put it here so we don't forget. So remember, a root times a root cancel, and you just get what's inside. That times that. This times that. And negative 1 times 1. All over, we're going to leave this in factored form, always. Okay? So what happens is these cancel, oops. And so I'm just left with an x on top. So this x, because that's being multiplied, will reduce with that. So really, we have the limit as x approaches 0 of, there's nothing on top, so I do need a placeholder, and it's all over this. So now I can try substitution again, and it's not undefined. The square root of 1 is 1, so 1 plus 1 is 2, and so we get 1/2. Okay, so that is some good algebra review. All right, you give your practice a go and see how you do.